Hi, my name is Gianmarco Iodice and I'm a GPU compute software engineer at ARM. I'm a part of Cambridge ecosystem visual computing team where my research interests fall into image processing, computer vision, machine learning and computational photography. With this presentation, I'm going to talk about a real-time implementation of a stereo vision algorithm on our Mali mobile GPU. Before jumping in the full details of the OpenCL optimizations, which concerns the main part of this presentation, I would like to give you a brief overview about the stereo vision. In particular, I would like to say something about what is a stereo vision, why it is useful, and the implementation adopted. After that, we arrive to the OpenCL optimizations, which concerns the main part of this presentation. At the end, the conclusion and future works will be shown. Let's start with the stereo vision overview. What is dense passive stereo vision? Stereo vision it is a really powerful visual sensing technique aimed at inferring depth by comparing two views of the same scene. But what does it mean? It means that if we have two cameras, we are able to capture the scene from two different points of view. For each point which is visible in both images, we can infer its depth. But in the title, we have other two keywords, dense and passive. With dense, we mean that we infer the depth for each pixel of the image. And with passive, we mean that we try to infer the depth for each pixel without using any structural light. Fields of application help me to say several, because nowadays stereo vision it is not only an interesting research subject, but it finds application in many real-world use cases. In automotive, for instance, for improving safety on board, in industrial application, in entertainment, for instance, for controlling with natural gestures, smart TVs, or for immersive gaming. But how does it work? Assuming those conditions, cameras optically identical, so same image sensor, same focal length, the cameras are horizontal aligned, the images are rectified, so no lens distortion, no barrel distortion, and the images are captured at the same instant, we can talk about an horizontal epipolar line constraint. What does it mean? It means that if we have a point which is visible in both images, that point lies at the same scan line but different x. The difference in x coordinates it is called disparity and is what we are looking for, because the depth it is inversely proportional to the disparity, and the relation is given by this formula, where the b, f, and peak sides are respectively the baseline, so the distances between the two cameras, the focal length, and the size of the pixel on the image sensor. Once we have the disparity for each pixel of the image, we have the depth map, and then we can back project the pixels in a 3D space, as you can see in the video of this slide. Okay, we have figured out that in order to know the depth, we need to know the disparity. One possible approach it is called local approach, and we need to face up the problem of correspondence. So we need to find the same pixels in both images. In the local approach, we define one image as a reference and one image as a target. For instance, if we define the left image as a reference and the right image as a target, for each pixel in the left image, we extract an n by n block around it, and we call it reference template. After that, we go on the right image and we look for the most similar block n by n at the same scale line, using a similarity measure such as sum of Hamming distance, sum of square difference, sum of absolute difference, and the disparity of each pixel is simply selected by the winner takes all, so the best match wins. Okay, the implementation adopted. We have three main ingredients in our recipe. We use grayscale images, so single channel. we adopted a multi-resolution strategy, also known as coarse to fine strategy. And we used the modified Census Transform 9x9 and 7x7 in order to improve the reliability of the disparity map under different light conditions. The modified Census Transform replaces each byte of the grayscale image with an NB string. The length of the NB string depends on the size of the modified Census Transform. In the case of 9x9 and 7x7, we replace each byte with 10 bytes per pixel for the 9x9 and 6 bytes per pixel for the modified Census Transform 7x7. In this slide, we have the pipeline implemented with OpenCL. So we start the computation of the disparity map at the coarsest level. So we have two images, the left and the right image. After that, we compute the modified Census Transform and we do the stereo matching on those on those modified Census Transform images. After that, we have two disparity maps, one using the left image as a reference and the right image as a target, and the other one using the left image as a target and the right image as a reference. After that, we have the disparity refinement stage, which removes out layers from the disparity map and tries to fill the occluded pixels with the nearest valid lower disparity. In the end, we have the upscale stage, which upscale by a factor of 2 the disparity map, which will be used at the next finer level as initial guess. This is repeated up to the finest level where we have the final disparity map. Before I mentioned the Census Transform, but what is it? It is a non-parametric local image transform which result does not depend on camera gain and light condition. It is really useful in stereo vision application, in particular when we want reliability under different light conditions. The Census Transform replaces each pixel by an NB string, which summarizes the local spatial structure. In particular, for each neighboring pixels, except the center one, it is associated one bit of that NB string. Each bit is set if the corresponding neighboring pixel value is greater than the center pixel value. In this case, we have an example. 115, it is greater than 78? Yes, so we set the first bit. 33, it is greater than 78? No, so we set to 0 the second bit, and so on. But for this implementation, we use the modified Census Transform in order to be robust also against the noise. It is an extension of the work did by Bernard and Frob. And instead of comparing the neighboring pixels with the center pixel, the idea is to compare the values of the neighboring pixels with the mean intensity value computed in the local window in the 3x3 window. So we have an additional stage before the modified Census Transform, which computes the box filtering 3x3. Okay, we have arrived at the main part of this presentation, which concerns the OpenCL optimization that we have adopted in order to achieve the real-time constraint on our algorithm. First of all, on Mali T600 and 700, we have OpenCL 1.1. But what is it, OpenCL? OpenCL it is a framework for writing programs in a heterogeneous system, which can be composed by CPU, GPU, DSP, FPGAs. OpenCL provides a standardized APIs for SIMD instructions, operations, APIs for memory transfer. It offers a built-in function library for mathematical geometric operations, really useful for improving the performance of the algorithm. The main key points of OpenCL on our Mali GPU are the image types are supported in hardware natively because we have a GPU. And the second key point is that the SIMD instructions are supported natively because we have an SIMD unit. So UChar16, UChar8 are supported natively in hardware. And this slide explains the main difference between a general desktop GPU and a mobile ARM GPU. Generally speaking, in a heterogeneous system composed, for instance, by a CPU and GPU, we have two different memories, one for the CPU and one for the GPU. What does it mean? It means that if we want a computation on the GPU, we need to move the data before starting the computation. But having two different memories, it introduces latency, and it increased the power consumptions because the memory transfer is not free. In an embedded system, it is really important to reduce as much as possible the power consumptions. And for this reason, on a mobile ARM GPU, we have physical the same memory for the CPU and the GPU. It means that we don't need to move data because we have physically the same memory. But in order to make the memory visible by both a CPU and GPU, we need to allocate the memory with CL create buffer and not with malloc. Other general advices when we start to program on an ARM mobile GPU. First of all, try to use as much as possible vector instructions because it can allow to execute less threads, and it can allow us to reduce the number of load store instructions. Try to use as much as possible CL built-in functions, in short, CL BIF when possible, because most of them are hardware accelerated. So try to use a mathematical CL built-in function instead of using your cosine or sine arctangent power of 2 or something like that. In the end, try to figure out what is your correct data types for your specific problem. Unsigned integer 16, UChar16, UChar16, because it has a big impact on the number of registers used. If we reduce the number of registers used, we increase the probability to execute at the same time a big number of work items. Further details and general advices you can find at malideveloper.arm.com, where you can find tutorials and videos about OpenCL and RenderScript. But in this presentation, we have adopted further optimizations. Let's start with the first one. Data layout. How we store data has a significant impact on the performance of the single kernel and the whole pipeline. It means that try to think in terms of the whole pipeline and not only in terms of the single kernel. Because most of the time, if we think in terms of the whole pipeline, we make other stages easy vectorizable. And this is the case because using a planar data layout, we are able to increase the performance of modified Census Transform by a factor of 1.4 due by the reduced number of store operations, the reduced number of arithmetic instructions needed for the swizzling. The important aspect is that it makes the serial matching stage easy vectorizable because each thread can compute the disparity for 16 pixels. Another important optimization, or suggestion I prefer to say, no serialization of CPU and GPU workloads. So try to avoid the serialization of CPU and GPU workloads in order to hide the driver overhead. What does it mean? It means that you need to try to keep the GPU busy while you are enqueuing the kernels in order to hide the driver overhead. But sometimes it's not enough, and it happens when we have several kernels to submit, and it happens when we have few threads dispatched for kernels. But some kernels in our pipeline could be executed in parallel. For instance, the algorithm has two independent flows, each one for computing respectively the left and right disparity map. What is the idea? The idea is, instead, for instance, to submit two kernels for computing the modified Census Transform on the left and right image, try to use a single kernel for computing the left and right modified Census Transform. One possible approach, assuming that both left and right image have the same resolution and same kernel parameters, is to use a third dimension of the global workgroup size for accessing the right element. So we have a single kernel for computing respectively the modified Census Transform on the left and right image. The important aspect is that it allows to reach the maximum GPU utilizations at a lower resolution, where otherwise few threads would be dispatched per kernel. Another important optimization. Try to do complex expressions instead of lookup tables. We have an example. The similarity measure used by the stereo matching stage is the sum of Hamming distance. The sum of Hamming distance returns the number of different bits into equal n-bit string. How can we implement it? Using XOR and the Popcount. The Popcount returns the number of ones in an n-bit string. We need to implement that. How can we implement the Popcount? One possible approach, it is a lookup table. It could be really fast approach on the CPU because we have a big cache, so if we fit a lookup table in the cache, it could be really fast. But it has an important drawback. It only has a scalar memory access. Another approach, it is the divide and impera, or called arithmetic parallel algorithm. It doesn't have memory access, and it increases the number of arithmetic instructions compared to the lookup table. But this approach is 3 times faster than the lookup table using vector operations. So the suggestion is try to use complex expressions instead of using lookup tables. In the end, try to avoid branches with padding bytes and CL built-in function. An algorithm with many conditionals is likely not to be optimal, but this is true not only on the GPU, it is true as well on the CPU. So we need to try to avoid as much as possible if-else conditions and loops. Most of the time we use if conditions for boundary check, for avoiding read or write out of memory. In these cases, try to use padding bytes instead of using if conditions. But sometimes if conditions are intrinsically in the algorithm. However, OpenCL provides important relational CL built-in functions that can be used for avoiding branches. For instance, the select, which is the ternary operator that we have in C, the all, which returns 1 if the MSB in all components of the vector x are set, or the clamp. In order to figure out how can we use the CL relational built-in functions, we have reported an example. In the disparity refinement stage, we invalidate some disparity in a disparity map, but we need to replace each invalidated disparity with the nearest valid lower disparity on the same scan line. In this case, we have the black pixel as an invalidated disparity, so we need to look for the nearest valid disparity and we need to choose the lower disparity. Okay, let's start to see a very naive approach. We have a while loop for looking for the nearest valid disparity. We have 3 different conditions, 2 for looking for the nearest valid disparity on the left and right side, and 1 for breaking the while loop. When we break the while loop, basically we need to select the lower disparity with the ternary operator. So if the disparity left it is greater than the disparity right, we need to select the disparity right as a good disparity. Another approach, it is based on select built-in functions and all. But what is the big advantages of using the select and all? The big advantages is not only related to the use of select instead of the if, because it makes the algorithm really vectorizable. So we can compute the disparity for 16 pixels at a time. So the big advantages to use CL built-in functions is also related to the possibility to vectorize our problem, as we can see in this case. For instance, the first two if conditions can be replaced with a select because are the right translations for that. The if conditions used for breaking the while loop can be replaced with the all. And in the end, the ternary operator used for selecting the lower disparity can be simply replaced with the select CL built-in function. This approach, it is 51 faster than the naive approach, so try to think in terms of CL relational built-in functions. We are approaching at the end of this presentation, so the implemented algorithm is easy to parameterize, is configurable in terms of disparity range. It computes disparity for the occluded pixels. The occluded pixels are those pixels which are visible only on a single image. As I said in the first slides, basically in the stereo vision we are able to compute the depth only if a pixel or point it is visible in both images. In our implementation we try to estimate the disparity or the depth also for the occluded pixels. The implemented algorithm is also offer good reliability throughout a wide variety of scene and illumination conditions, thanks to the modified Census Transform. In terms of performance, the system was sped up on the developed platform featuring an ARM Mali GPU and is able to compute at 120 frames per second with 60 disparity levels at 320 and 240, and is able to compute the disparity maps at 52 frames per second with 60 disparity levels at 640, 480. Moreover, we have tested the algorithm without using the multi-resolution strategy, and we are able to achieve real-time constraint also in these cases. We achieve, for instance, 49 frames per second with 60 disparity levels at 320, 240. In this slide we have reported some disparity maps that we have obtained by our algorithm, and in terms of accuracy we are close to the real-time Census Transform. The dataset is from the Middlebury website, which is the reference point for all stereo vision algorithms. Okay, but we have just started to play with the stereo vision and we want to improve the performance, we want to improve the accuracy of our algorithm. The idea is to use the sparse modified Census Transform 7x7 in order to improve the performance, because with the sparse modified Census Transform we are able to reduce the number of load, store and arithmetic instructions. But we need to take in consideration the more erroneous disparity using this Census Transform. In order to overcome this problem, we want to use a median filter and a weighted median filter in order to improve as well the reliability of the disparity maps. Final considerations about the stereo vision algorithm implemented on the ARM Mali GPU. The results reached by the GPU compute on ARM Mali are definitely promising for stereo vision applications, demonstrating the feasibility to achieve real-time performance on ARM Mali mobile GPU. Another important consideration is that small changes in OpenCL code can lead to rich big performance. A significant example is given by the data layout, because in that case we didn't introduce any tricky OpenCL optimizations. We have only rearranged data in such a manner in order to make our problem vectorizable. So remember, small changes in OpenCL can lead to rich big performance. In the end, well-optimized data layouts and types can help to reduce the size of the kernels. Keep it simple, keep it short, because it may reduce the number of registers each kernel needs, allowing more work items to run on the GPU at the same time. Another example is given by the stereo matching stage. Thank you for watching this presentation, but before finishing, I would like to say thanks to the University of Pisa, because this project was developed with a joint cooperation between ARM and the University of Pisa. In particular, I would like to say thanks to the professor Roberto Saletti for his cooperation and for his help on this project.